All right. Thank you everyone for coming to this seminar. So this is our first seminar for this quarter. So it's my great pleasure to have Dr. Dan Roy from University of Toronto and his students to come to visit us virtually and kick off our seminar for this quarter. So Dan is a Canada C5 AI chair at the Vector Institute and associate professor in the Department of Stats, Computer Science, and Electrical and Computer Engineering, and Computer and Mathematical Science. So Dan's research spans machine learning, mathematical statistics, and theoretical computer science. And very recently, I think Dan has been very actively working on theory of deep learning and a lot of topics in theoretical machine learning. And this paper, as you can see from the title of the talk, is a joint work with two of Dan's students, Blair and Jeff. So let me give a brief introduction to Blair as well. So Blair is a PhD candidate in the stats department at University of Toronto, supported by the Vector Institute and a NSERC doctoral Canada graduate scholarship. So I assume it's a very prestigious scholarship.
It is.
Blair received his bachelor's degree in financial mathematics from Western University in 2018. His current research area is broadly in statistical machine learning with a focus on theoretical performance guarantees for sequential decision making, which is exactly the main topic of today's talk. All right, so please join me in welcoming Dan and Blair and Jeff to give this talk.
Thank you very much for that introduction. So I'm going to start this talk off, and then Blair is going to take over. I organized Blair to come and present this work in recognition of the fact that it's free for him to travel virtually with me to UCLA, and Blair and Jeff did the vast lion's share of the work here, and he's the expert in the world on this subject right now. So I'm going to jump into some background, and in particular, I'm going to launch off with a simple example of trading stocks. All right, so the problem is that you need to invest your money into a stock portfolio. And we're going to imagine that we're in a situation where you have access to several market experts that can give you advice. And the form of that advice is you can watch their stock picks. And your goal is you can mirror what they do. You can say interview them and pick who you think is strongest and stick with them the whole time, or you can try to do something more clever and jump around them based upon how well they're performing. At the end of the day, you're going to measure how well you've done in terms of regret. So you're going to one of those experts is going to be the best possible expert, and you're going to hope that you're doing almost as well as them. And if you're bouncing around and you do a lot worse than the best one in hindsight, then you might regret that. So that's the origin of that term. So how might we design a strategy in this case? The starting point of, say, designing an optimal strategy will be some sort of assumptions. And so we could say start where they have in kind of classical finance with a simplifying assumption on, say, the returns. We could say assume that the log returns are a geometric Brownian motion, which would be something like kind of like almost like Iid Assumption for the stock movements. And we could then derive an optimal response based upon that. However, as we've seen, say, recently with GameStop and all the craziness in the market, sometimes the market is not driven by non-stochastic forces. And so we have we have a nice model. You can drive an optimal response, and then but maybe it's not always a fair place to start. So where would we go if we're going to abandon the Iid assumption? Where would we land? You could go all the way to the other extreme and make an adversarial analysis and assume that the world is out to get you, but you're going to pay a cost for that for being that conservative. And we would argue it's certainly too much. And you can think of this, this stock market example, you can think about it as like sort of an extreme form of just ordinary statistical modeling. I want to make modeling assumptions, but I don't actually believe my model. If I believe my model too much and I drive an optimal response, it might be rather fragile to violations of the modeling assumptions. So in this particular situation, is a departure from IID-ness benign? And how would we quantify that? And that's, we could think informally in terms of the influence of these non-stochastic forces being small if we don't move the market. But then just kind of leads to the question, what does it mean to be small? At the end of the day, whether we're doing statistics with models we don't believe or say trading stocks, we want to maximize profit without having to know what exactly is driving the market. Are we in this nice stochastic setting, getting IID data? Or is the world out to get us? Or are we somewhere in between? So we're going to pursue this question of how to behave when we don't know what's driving the data we're going to use the framework of sequential prediction with expert advice. So there are some experts in the audience, but I'm going to just introduce it for the sake of everyone else. So I'm going to start with sequential prediction on its own. So this is going to proceed in rounds. And on each round, some event is going to happen, and we want to make a prediction beforehand. So that's going to be our prediction. And that prediction can be based upon historical data we've collected up until now. Then the outcome happens, we make an observation, and we incur some kind of loss. Okay, so this is gonna be like, predicting a stock movement. The stock movement happens, and we incur some loss from having made a trade or not. Now, with expert advice, when we talk about sequential prediction with expert advice, what that means, just before we make a prediction, in addition to historical data, we get these experts' predictions, and we can incorporate these into our own policy. And the one other thing I'll discuss in a moment is we're also going to be using experts as benchmarks. We're going to be, in some sense, trying to compete with the experts and do as well as they are. Now, so just to kind of explain how information flows in this problem, on the first round, we have the experts' predictions, and there's not much historical data. There's no historical data at that point, so we just have to make a prediction based upon what, say, the experts are going to do, and our own hunches say. At the second round, we have the historical data of one round, and we get the new expert predictions. We can make our predictions, and we incur some loss, and so on and so forth. Right. So at any particular point when we're making a prediction with the entire history of what's happened, with the entire history of expert predictions and so on. And we also have the expert predictions at that round. Now, how do we measure performance in this setting? So we're going to measure players' performance in relative terms, relative to the class of the N reference experts. Okay, so we're not only seeing their predictions, but we're going to be measuring how well we're doing relative, or in terms of how much excess cumulative loss we've incurred compared to the best single expert in hindsight. So we're not comparing against, say, who did the best on each round and summing that up, but rather like, if there was one expert we could have stuck with the whole time, then we're going to regret having not just stuck with that expert and not tried to bounce around and do something more clever. So in math, this is written like this. The first term there is a cumulative loss that we've incurred with our decisions, and then we have the best expert in hindsight. So in a worst case analysis, this prediction problem is called online learnable if we can develop a strategy that leads us to incur only a sublinear regret. So if you think about normalizing these terms by 1/t, that's going to mean that our average per round regret vanishes. So in some sense, you're kind of performing almost as well on average as the best expert. Now, in our case, we're going to go beyond this worst case analysis, and so we're going to be thinking also about the data being potentially distributed in a nice way, or somewhere in kind of intermediate between adversarial and Iid. And since expectation is going to be doing a little bit more work for us, besides the randomness potentially in our strategy, which you would expect to appear potentially in an adversarial setting, we're also going to be thinking about potentially the experts' predictions being stochastic and the data generating mechanism also being stochastic. And there can potentially be collusion between the experts and the data generating mechanisms. Right, so this can be complicated, just to say. So this is it's not a vanilla Iid measure that we're taking an expectation with respect to. Now, what does it mean to be optimal in this setting? So I'm going to talk about two extremes. So and two settings. So one setting is a stochastic with a gap setting. In this setting, the expert predictions in the data are Iid over time. Okay, so maybe the underlying situation is drawn Iid. The experts react in some kind of fixed way each time, and they render their decisions, et cetera. And we're also going to, in order to characterize the hardness of a stochastic setting, we're going to introduce this variable delta, capital delta, which measures the gap between the best expert in mean loss to the second best. Okay, so we call this the gap. Now, in this setting, it's known, and this is fairly recent work, that, it's known that there's a constructive algorithm which achieves the minimax regret in the setting. So you can do as well as possible in the worst case, subject to the assumption that delta characterizes what the gap is between the best expert and second best expert. And what is the minimax regret? How much regret are you incurring? So actually, you're incurring a constant in number of rounds regret. So it's uniformly bounded in how much you're interacting with this, which means eventually you stop incurring regret. That's what that means. At the end of the day, how much regret will you have incurred in the long run? Well, it's going to be log n over delta. Okay. So at the other extreme, opposite of stochastic is adversarial, where the experts in the data are out to get you, and they are deciding what to do based upon your strategy, which they know. Now you might have some private randomness, which they don't know, but let's not get into that complication. So in this setting, it's known that there's also a simple algorithm that achieves the minimax regret. And what is that minimax regret? Well, after 2 rounds of interacting with these adversaries, you can guarantee your regret is growing no faster than root t log n. Okay, and that's also a lower bound matching. All right, so these are the 2 extremes. They're quite far away from each other. If I'm in a situation, I might not know which situation I'm facing. And so you might ask, is there a single algorithm that can kind of be placed into an environment where these are the 2 possible situations it faces and say perform as well as possible, meaning meet the minimax regret no matter what? So the answer to that question is actually yes. And this is recent work. So let me just describe this graph. So the algorithm that achieves this simultaneous minimax regret in both these scenarios is called Hedge. It's also known as like multiplicative weights and various other names for this algorithm. It's been reinvented in maybe 6 or 7 different fields. And here's its performance. This is actually a simulation that Blair and Jeff ran. And so if you put it into a stochastic environment where it's being fed IID data, you see the lower curve, which plateaus. Essentially, it kind of works out what's going on and no longer incurs regret in the long run. And then in the adversarial setting, it incurs the square root t log n regret. And so showing that Hedge was simultaneously minimax in both of these settings is a result of Murtada and Gaifa recently. Right. Now, this is beautiful, and it would seem to answer the question we started off with, which is like, how do we behave in a situation? The real data are not stochastic. That's too optimistic. Real data are not adversarial. That's too pessimistic. And so we're really somewhere between. And so the guarantee that we have for Hedge is not sufficient, right? Because we want to do well for, like, say, almost I-80, whatever that means. So we build off a framework introduced by Rachlin, Shadari, and Tawari, where we're studying a spectrum between stochastic and adversarial. Okay. So we've extended this to deal with this kind of fully adversarial setting that we want to deal with as well. And the idea is that we're going to fix a neighborhood of kind of allowable distributions. And then at each round, the data that we're going to be presented with are going to be drawn from arbitrary distribution, which is constrained to live in this neighborhood. So here's a picture of the 2 extremes and then this kind of intermediate regime. So in the stochastic regime, these triangles here are representations of the space of all probability measures on data and experts, if you will. Okay. And so in stochastic, the line is going through the exact same point at every single round, which is to say that the distribution at each round is the same. So that's IID. In the adversarial setting, the line is bouncing between the extreme points. Now, what are extreme points? Extreme points here are distributions that are not random. They're like degenerate distributions. So this is an adversary hand-picking the data to make you do as badly as possible. And then what's this third setting? This is a setting we study, which actually includes the 2 settings I've just described as special cases. We have a convex set that's indicated by the green, and the adversary can bounce around this convex set any way they like, but they have to stay within the convex set. So that's what we're going to study. And that's going to be how we interpolate. So we're going to be in a setting. There's going to be some convex set. It could be the whole triangle, in which case we're in the adversarial setting. It could be a single point, in which case we're Iid, or it could be something in between. We're not going to know what situation we're in, but we want to perform minimax optimal no matter what situation we're in. We'd like to ask, right? Now, Blair and Jeff set off thinking that they were going to be able to show that Hedge was minimax optimal once again. Okay, so I won't tell you I won't ruin the story yet. So let me just explain a bit more formally what we're aiming for. So we're aiming for an algorithm that's robust to a spectrum of data generating mechanisms. And that's formalized in terms of so-called adaptive minimax optimality. So we'd like the algorithm to achieve minimax optimal performance in each setting without requiring knowledge of which setting it's been placed into. And the way you formalize this is you give a set, say lambda, which is the spectrum of settings you want to be able to handle, like, you know, so, say an arbitrary, the set of all stochastic settings and the set of all adversarial settings, right? That would be one. But now we're going to enlarge that to these convex constraints. And if we know theta, we're going to let r star theta denote the minimax regret, the best achievable performance. And what we wanted to do is we want to design an algorithm whose regret, r theta of t, is no more than a constant c, more than the multiplicative constant c, more than the minimax optimal regret. And we want that bound to hold uniformly in all theta. And that uniformity is formalizing the idea that this has to hold without knowledge of which situation we're in. So that's how you formalize this idea mathematically. All right. So I'm at a place to hand it over to Blair so he can present his work with Jeff. Blair, take it over.
Great. Thanks, Dan. Okay. So now that Dan has kind of described the setting that we're living in and what it means to do well in this setting with adaptively minimax optimal, let me give a kind of overview of what we do in this work. So the first thing that we show is that Hedge is actually suboptimal in between these two endpoints. So Dan gave a bit of a spoiler earlier about the idea that it's not optimal in between stochastic and adversarial. And this was actually surprising for us. You know, we initially set out hoping to show that Hedge was going to be optimal at kind of all scenarios in between. But it turns out that if you don't have oracle knowledge, so by that we mean knowledge of what this constraint set's going to look like in advance, where you could then use that to tune your algorithm, without that, Hedge cannot be simultaneously optimal at all settings in between the stochastic with a gap and the adversarial case. So what we do is we provide a new algorithm that does achieve the minimax rate in all settings, and it does so without having to know in advance which setting it's living in. So by definition, this algorithm is adaptively minimax optimal, and we call it Medicare. I'll describe the algorithm a little bit later in the talk. But first, let me go into a little bit more detail of what this positive result looks like for Medicare. So what are the adaptively minimax optimal rates? So first, remember that Dan said in the adversarial case, the minimax optimal regret is square root t log n. So t here is number of rounds, n is the total number of experts that are being competed against. So if someone told you in advance that some subset of these experts would only be good and the rest you could ignore, then you would just play your adversarial algorithm on this small subset of size n0, and you would incur regret of root t log n0. So we might hope to be able to achieve this without even having to know what this smaller subset looks like. Similarly, if we know in advance that one of the experts is going to be better, but we don't know which one it is, we just know that it's going to be separated by some amount from the rest, this is almost the stochastic with a gap case. I say almost because we're not even making an Iid assumption here. We're just saying on each round it's better in expectation by some amount delta. And then we would hope to be able to still achieve constant in t regret, so where it's looking like log n over delta 0, which is the regret that is minimax optimal in the stochastic case. And indeed, that's exactly what we show. So we show that the adaptively minimax optimal rate of regret, when there's only one expert that can be the best, so n0 equals 1, we get constant in t regret. And if we have more than one expert, we need to have regret that depends on t, but it now changes with the number of good experts here. So this n0 term, and so obviously this is better than root t log n. So it kind of interpolates between these two cases, because of course, when n0 is equal to 1, then this log n0 goes away, and you pay for this kind of constant term. And Medicare actually achieves this adaptively minimax optimal rate without having to know in advance what n0 is, delta 0 is, or anything about these constraints. So now let me describe a little more carefully what we mean by relaxing the Iid assumption. So we've kind of given some intuition for what it is in between, but let's formalize exactly what we mean by that for what these n0 and delta 0 terms look like. So we call this setting time homogeneous convex constraints. The intuition here is that the experts and the environment are able to collude. So at each round, the kind of joint realization of experts, which are the x's here, and data, which are the y's, are sampled from some adversarial conditional distribution. Adversarial in the sense that the environment gets to pick it to try and make the player have bad regret, and conditional on kind of everything that's happened in the game so far. So that flow of information Dan went through. A little more formally, we can think of this as fixing a convex set of distributions ahead of time, which is a subset of all the distributions over experts and data jointly. And then at each round, the experts and data are drawn from some element of this set D, where the element gets to be chosen using the history up to that time. So we call this time homogeneous because the set D does not change over time. That would certainly be an interesting setting where you could think of this constraint set shifting, but we do not allow that. We require D to be kind of fixed ahead of time, although the player doesn't know what D looks like. And it's convex, which is not that strong of an assumption. You can think of if D was not convex and the environment was trying to pick between two distributions that they wanted to use at that round, if they all also have access to a coin to flip to make their decision, they immediately have access to the convex hull. So we just realize that we have to compete against the full convex hull of these distributions. And there's going to be adversarial. Yeah, absolutely.
Yeah, so what do you mean by a convex set of distributions? So can you explain it a little bit more?
Yeah, so I just mean that in distribution space, this is convex. So if I take any mixture between the two distributions, it's still in the set.
Okay, so why do you want to make this assumption?
So we actually need it for our results. Our results rely on a Minimax theorem that uses convexity quite heavily. So it's needed in our analysis. And then what I'm saying is that it's not such a kind of strong assumption to make, because if you don't have a convex set, it's pretty easy to imagine that the environment can kind of have access to the whole convex hull by just having access to some way to mix between distributions.
I see. Okay, thanks.
Yeah, no problem. And so in particular, we're thinking of the environment choosing the distribution in the set D in order to maximize the regret of the player. But of course, they're constrained in how adversarial they can be by what the size of this D looks like. So these sets D are kind of obviously very general, and they might be quite difficult to describe for any particular application of interest, right? It could be.
Yes, sorry, may I ask a question?
Yeah, for sure.
Yeah, I also have a question about the convex set of the distribution. When you say the mixture of the distribution, do you mean the mixture of the density function of the probability or?
Oh, so sorry, it's not the individual distributions themselves that have to be convex. It's that I have a collection of these distributions, and that collection itself is convex. So convex is a property of the collection of distributions, not a property of the individual distributions.
Yeah. I mean, whether these distributions are or have the density function.
Oh no, we don't assume that. They can be. It's just the measures.
Okay.
So just their probability measure.
Okay. Thanks.
Yeah. So as I was saying, the set D can be quite complex to describe. So we want to be able to characterize this set D using some quantities that satisfy a few key properties. The first of these is that we want to be able to simplify kind of this abstract complexity of the constraint. So we want to have quantities that make it easier to verify, is this a reasonable constraint to consider for this type of problem? And these quantities should also differentiate whether the data is easy to learn or not, and they should do so independently of how the predictor is going to play, so what algorithm they're going to use. In particular, easiness is kind of an inherent quality of data, not of data algorithm pairs. And this is often kind of glossed over or not a point that's made in the literature, but we find it important to kind of emphasize. And finally, of course, we want these quantities to be rich enough that they give us matching lower and upper bounds on regret. It's not very useful to get quantities that don't tell us anything about performance. So the first of these quantities we call the effective experts. So this is a set, and it's a subset of all of the experts that the player has access to. And in particular, it's the experts that are optimal in expectation for some element of this set D. So if we think of picking any mu and D, so this is just a distribution over experts, Some of the experts are going to be best in expectation under that distribution. It might be just one of them, or some of them might have the same expectation. And then we can union over all of the distributions in D, and we get the collection of all of the experts that are optimal in expectation for some distribution. And often, we're actually interested in the number of effective experts, which is just the size of this set. So this is analogous to the setting when there's a single best expert in the stochastic with a gap case. Then, of course, this I0 set is just a singleton. The other quantity that we use, we call the effective stochastic gap. So this is a little bit more difficult to explain, but the idea is it's basically how separable are these effective experts from the rest of the experts. So how difficult is it to kind of tell the difference between these two subsets of the experts? And more precisely, what this says is for any distribution mu that we have in our set D, we have an expert that's best in expectation, and we can compare them to the best. We could compare them to the second best, but instead we're going to compare them to the best that is not one of the effective experts. And then we say, what's the minimum that this distance is over all of the distributions mu in the set D? And so this is kind of the amount of resolvability between these effective experts and the ineffective experts. And so this is analogous to, in the stochastic setting, the regret is going to depend on basically the gap in expected loss between the best and second best expert. So we're just kind of generalizing that to our notion of effective experts. So again, these quantities are a bit general, maybe definitely not internalize them just yet. So let me walk through a simple example to kind of emphasize what they look like a bit more. So in this example, because the way the quantities are defined are in terms of how much loss the experts are incurring, consider our set D just being jointly defined by some parameter alpha, so that when we know alpha, we know exactly what distribution we're talking about. Now, we're only going to have 5 experts here. I'm telling you that the odd experts are effective, and I'll explain kind of why that happens throughout the example. So let's visualize what this looks like. On the x-axis here, we just have this abstract parameter alpha changing. So this corresponds to the distribution we're picking from our set D. And the y-axis is plotting the expected loss of the experts. So each of these lines corresponds to an expert, and it tells us what's their expected loss if we fix this distribution. In particular, if I picked some alpha 0 in from my parameter here, that corresponds to picking a distribution from D, and then I know what the expected loss is of each of the experts under that distribution. So if I was in the stochastic with a gap case, so where the data is generated IID at each round, and say it was IID from the distribution that corresponds to alpha 0, the gap I would consider is between the best expert and the second best expert. But as I mentioned, we're actually interested in the effective stochastic gap, which is going to be between the best and the best that is not already an effective expert. So I haven't told you why yet, but I am telling you that this expert 3 is effective, which means we get to kind of leapfrog over them, and we just have to compare between the best expert here and the best that isn't an effective expert, which corresponds to expert 2 for this example. And so you see that we actually have a larger gap here, which is nice, because it means that kind of the effective experts and the ineffective experts are more separable than just the best and the second best in this case. So now how do we tell which experts are actually effective? Well, I can just highlight what the minimum expected loss is under each of these alpha values. And I see that for alphas over here, expert 5 has the best expected loss, then it's expert 3, then it's expert 1. So any expert that gets highlighted here is an effective expert, and any that don't are obviously ineffective. And so that's 2 and 4. And then the effective stochastic gap is just going to be the minimum distance from this highlighted line to the ineffective experts, so to the red line here, which in this setting ends up happening at a corner here. So we see this ends up being the actual effective stochastic gap for our set D. So hopefully that made it a little bit more clear what these two quantities end up looking like, but I'm going to run through a few more examples that are kind of illustrate how this describes a spectrum between stochastic and adversarial. So first, the stochastic with a gap case. So in this setting, we have IID data again, and we can think of this set D as just being a singleton, some mu naught, which the adversary has no choice but to sample data from at each round. Kind of by design, we expect that there's only a single best expert in expectation. So there's only one effective expert, and it's by definition the one that's best. And then our effective stochastic gap is just going to be the expected difference between this best expert and the second best expert. At the other extreme here, we have the adversarial setting. So in this case, D is the set of all distributions that are over experts and data jointly. So back to Dan's kind of cartoon picture, this is where that green set is kind of the entire triangle. And importantly, this contains point masses, so we can handle the usual kind of deterministic adversary that often is studied in online learning. Here, the number of effective experts is all of them, because we can always pick a distribution where one of the experts will be best. And our effective stochastic gap is infinite, which is by convention, because we have an inf over an empty set. Another interesting setting is the adversarial with an expectation gap, which is from Mortada and Gaifa paper. So here, think of fixing kind of some expert ahead of time, and then looking at all of the distributions where that expert is best in expectation, and they're best by some amount delta. So by design, because we've just fixed a single expert, we have n0 equals 1, a single effective expert, and we've also chosen this delta to be kind of the resolvability between that best expert and the ineffective experts. And finally, kind of the most intuitive example, I think, is this neighborhood of IID setting. So here, imagine fixing any distribution you want in the space of distributions over experts and data jointly, and then describing some small ball around them, so a ball of radius r. And this ball is going to be our set D. Let's also suppose, just for simplicity, that this mu0, all of the experts are kind of distinct in that, so they all have different expected loss. Then the number of effective experts and the effective stochastic gap will depend on how big this ball is, what the radius looks like. And it'll depend on it in a slightly more complicated way, so let me dive into that a little more carefully. So recalling the setting, we have the set D is just a ball of some radius, and our experts are all kind of distinguishable under this center distribution. Then let's look at how first the number of effective experts is going to change as we change the radius of the ball. So when the ball is 0, the set is just a singleton, so we're in the stochastic with a gap case, and so we have one effective expert. Now, as the radius increases, this basically corresponds to letting these expected losses kind of wiggle back and forth. They can be moving around a bit, but the first expert here is kind of still always the best until we've let the radius increase enough that the first and second experts could potentially switch places for one of these distributions, at which point the second expert now gets added to our set of effective experts, and we now have 2. And then the radius is going to continue increasing until eventually the third expert is able to actually swap places. So that means that the expected losses are able to wiggle even more, and then we're going to add another expert to our set of effective experts. So in particular, as the radius increases, we can only be adding effective experts. None are going to fall out. Our set's only getting bigger. And it's going to increase discretely. So it's going to be flat until we reach kind of these specific points where the expected loss is allowed to wiggle enough that the experts can swap places. And then we get to add a new expert to our set. Now we're also interested in how the effective stochastic gap is going to change. And I'm going to plot the reciprocal effective stochastic gap, because that's what actually shows up in the regret bounds. So consider here, again, when the radius is equal to 0, we're in the singleton, we have some gap. This is just the expected loss between the first and the second expert. Now, as this radius increases, again, these expected losses get to become closer together, which means that the kind of resolvability between the first and second experts gets more difficult. And so the reciprocal stochastic gap is tending to infinity at an asymptote here, because the stochastic gap is tending to 0. And so we see that if we have n0 fixed, then within that kind of sliver where n0 is fixed, as the radius increases, the reciprocal stochastic gap tends to infinity. But then as soon as we reach the point where we add another effective expert, we're going to see it reset back down to some finite point. And that's because the effective stochastic gap only compares between effective and ineffective experts. So once we add an expert into the effective set, we no longer have to compare with it. So our effective stochastic gap drops down. And then we see it increase again, and then have another drop where we have a reset when we add an effective stochastic, an effective expert. So what this does is it means that we have a lexicographical order on n0 and the reciprocal stochastic gap, by which I mean that for nested Ds with respect to this order, so where we order them by n0 first, and then within n0 being fixed, we would order them by the reciprocal effective stochastic gap. It means that larger sets are going to be harder to learn. And so this means that these two quantities have kind of achieved our goal of quantifying how difficult it is to learn this data based on what the kind of constraint set looks like.
So can you explain a little bit more why the effective gap will drop whenever?
Yeah, so
yeah,
if you imagine just having 3 experts, say, then as this kind of radius first approaches this point here, the difference between the first expert and the second expert is getting smaller, and that's what the delta 0 is measuring. So that value is getting smaller, and it's tending off to infinity. And then as we reach the point where first and second can kind of swap places, so the second expert can be optimal in expectation, then that second expert is now in our set of effective experts. And that means we no longer are comparing against the second expert. So then when we reach this point of the radius right here, we're going to say who's best in expectation, and we're only comparing them to the third expert, who is now separated away from these kind of first two experts. And so we're going to see like a reset in the sense that we were comparing between, say, the first and second expert. And then when we reach this point, we're now comparing between the first and the third expert all of a sudden, because the second expert has become effective. And so that is going to constitute kind of a larger delta again.
So I wonder, is this plot can accurately reflect the for example, the ranking of this if expected risk for each expert? Because for example, why when you add in,
So this is hiding something,
so for
which
example,
is that this delta 0 is a minimum over kind of all the resolvabilities. But of course, each expert has their own resolvability between themselves and kind of the best, the effective experts, right? You can think of there's a gap between the first and second, the second and third, third and fourth. And so it would be a little bit more precise if we kind of described it in terms of each of these individual gaps. But then it gets a bit confusing to kind of keep track of which gap corresponds to which expert. So I've kind of hand waved a bit by stating things just in terms of this kind of minimum stochastic gap. But you're right that to be more precise, it would matter on kind of the gap for each of the experts.
Okay, thank you.
Yeah. So as he's pointed out, it's a bit strange to see this reciprocal stochastic gap tending to infinity. And in particular, you're probably asking, what does this mean for the regret? So let me go into that a little more carefully. So recalling the plot that Dan showed earlier, which is comparing the hedge algorithm in the stochastic and the adversarial settings. And I can be a bit more precise in the legend here, so that for the yellow line, we have just a single effective expert. And on the red line, we're talking about the adversarial case, where the number of effective experts equals all of the experts, which in this simulation example is 1,000. So how does the reciprocal stochastic gap show up here? Well, I can plot this dotted line here, which roughly corresponds to log n over delta 0 squared. I say roughly, there's a couple constants that I've hidden. But basically what this line corresponds to is how much time it takes the algorithm to figure out that it's in an easier setting, to figure out that there's only a single effective expert. Up to this point, basically in both the adversarial and the stochastic cases, hedge is incurring adversarial regret. It's growing kind of like square root t log n here. And then once it reaches this point, it's kind of gathered enough data to have been able to adapt and to have identified that there's a single effective expert. And then it's going to basically get constant regret from that point out. It basically only occurs the regret that it incurred up to this point. And in the adversarial setting, it continues growing. And so as this delta 0 tends to 0, which means that the reciprocal gap is tending to infinity, it is not that regret is tending to infinity, but just that this dotted line is moving farther out on our x-axis, which means that it's going to take longer for the algorithm to identify that it's in a kind of easier setting, the stochastic setting, and so it's going to incur adversarial regret for longer. But for any kind of finite delta 0 that's strictly positive, eventually it will flatten out. It will just mean it will take longer for it to stop incurring adversarial regret. So what does this look like in the kind of intermediary stage? So now I've plotted the one of our kind of new settings, which is where we have two effective experts. So this is not stochastic and this is not adversarial anymore. It's somewhere in the middle. And I've plotted it with our optimal algorithm Medicare. So as promised, its regret lies in between this stochastic and this adversarial case and grows like root t log n0. Here, n0 is 2. But we see again that for some initial period of time, it has to incur adversarial regret. And that's because the algorithm needs to figure out that it's in an easier setting where there's only two effective experts, and it's basically got to adapt to that. And so up to that time, it incurs adversarial, and then it adapts and it starts incurring a smaller amount of regret than in the full adversarial case. And this is also going to be dependent on the effective stochastic gap. So it follows the exact same type of idea, whereas that reciprocal stochastic gap tends to infinity, it just takes a longer amount of time for the algorithm to start incurring root t log n0 regret instead of root t log n. And finally, just to kind of emphasize the difference between hedge and Medicare here. So again, I've plotted hedge in the adversarial setting. That's this red line up here. So that's root t log n. And then I also have plotted now hedge in the kind of intermediary setting. So when we only have two effective experts, where we would hope that it could kind of adapt to that case. But as I mentioned before, it cannot adapt. So it ends up incurring this pink line, which is basically exactly overlapping the adversarial line here. so that it basically doesn't get any benefit of the fact that it's in an easier setting, and it incurs adversarial regret, whereas our algorithm, Medicare, lies in the middle here. It's getting root t log n 0. And finally, Medicare in the stochastic case, so when there's a single effective expert, basically looks just like Hedge. It also reaches a point and then levels off to constant regret. And I haven't plotted Medicare in the adversarial case because it'd get a bit busy, but rest assured, it also follows this red curve. So it would be achieving the right rate in the adversarial setting. So this is kind of a single simulation example to convince you that Medicare is optimal in kind of all of these settings at the same time. But now let me describe what kind of our theorems look like that give some mathematical formalization to this simple simulation that I've just demonstrated. So first, let's talk about the Hedge algorithm here. So a bit of bookkeeping. We're only going to be considering finite expert classes, and we're going to suppose that our losses are bounded. So without loss of generality, let's just suppose that they're in 0, 1. And we're also going to be talking about proper algorithms. So a proper algorithm is one where instead of making an arbitrary prediction from your prediction space, the algorithm looks at the experts it has available to it and picks one of them to emulate, by which I mean play exactly the prediction that that expert has played. One way to visualize this is that the algorithm assigns a probability distribution over experts, which is this weight vector W, then samples an expert according to this and is going to play the prediction that that expert says. This might seem a little bit limiting, but it turns out Hedge is a proper algorithm. Our algorithm, Medicare, is also proper, and our lower bounds apply to both proper and improper algorithms, which basically says that in this setting of finite expert classes, it's sufficient to consider proper algorithms to get the minimax optimal rates. So the Hedge algorithm I'm going to describe by how it chooses what this weight vector W is. So it's going to be parameterized by a learning rate schedule eta, which corresponds to the learning rate it's going to use at each round. Let's initialize the weights as uniform. A bit of notation, the loss of the ith expert at time t is going to be this little l, and the cumulative loss of the ith expert is just going to be denoted by this capital L up to round t. Then the weights for Hedge are defined using an exponential update rule. So the weight of the ith expert at round t is proportional to. Proportional is just hiding that we have to do some renormalization over the finitely many experts. The exponential of the learning rate times the cumulative loss of that expert. So if this cumulative loss is large, that means that the expert has not done very well so far in the game, and so we don't want to put much weight on them. And vice versa, if the loss is small, then that means they are doing well at predicting, so we would want to have a higher chance of emulating them. And the way that we trade off whether the loss is kind of large or small is encoded by the fact that we're using an exponential update rule and what our learning rate is going to look like. So we're going to consider Hedge of the form where the learning rate is some constant c over square root of t. So this is called decreasing Hedge, and this is kind of the standard Hedge algorithm that we would think of. Sometimes you see that this, instead of a little t here, there would be a capital T for the total number of rounds. Having a little t here just lets you kind of adapt to the fact that you don't want to have to know what capital T is in advance. You want it to kind of work as long as you let your algorithm run for. And we're also going to suppose that some set D has been fixed ahead of time, but Hedge maybe doesn't have access to that. So recalling what n0 and delta 0 are, we prove that if you take this constant c in the learning rate to be square root log n, so this is the optimal learning rate to take in the stochastic and adversarial endpoints. This is the learning rate they use to prove that. Then in the single effective expert case, Hedge does get the right thing. It gets the constant in t rate of log n over delta 0. And so this matches what Mortada and Gaifa showed for their stochastic case. But as soon as we have more than one effective expert, no longer, it basically fully has to incur the adversarial regret. So it immediately jumps up to root t log n and has no dependence on what n0 is. So we see there's essentially no adaptivity of the Hedge algorithm in any of these intermediary settings. Now you might think, well, what if I just take a different learning rate? I can take my c to no longer kind of depend on n in this way. And then we do see some adaptivity to what the number of effective experts is, but it's not the optimal adaptivity. Basically, we know that we can get this log n0 underneath the square root, and so seeing it outside here, it's not optimally adapting. And also, in the case where there's only one effective expert, it has a log n squared over delta 0 instead of a log n. And we also prove matching lower bounds for this. So this is not like an artifact of our analysis. This is basically the limitations of how well Hedge can do. So it can't adapt to this kind of intermediary settings. And so that's the case where Hedge doesn't know what this set D is. And that's the case we want to live in. We want to define algorithms that are optimal regardless of what the setting is without knowing what setting they're in advance. But we also would like to know kind of what are the limits of performance, in which case we can say, how well can Hedge do if I told it in advance what this set D looks like? So in particular, if Hedge can take its learning rate to depend on square root log n0 in this way, then it does achieve the right dependence on n0 in this case. So it gets root t log n0 instead of having the log n0 outside. So this is not really kind of nice for Hedge because we don't expect to know what n0 is in advance, but it does tell us that we can expect to achieve this in the case where there n0 is between 1 and n. And so we hope to describe an algorithm that does achieve this without having to know in advance what the constraint set is. So in all of these bounds, we have terms depending on two different things. So the first is t, which corresponds to the long run regret accumulation. So that's basically the line after the dotted line in the simulation plot. That's what it looks like once the algorithm has adapted or not adapted in Hedge's case. And the other term depends on log n and the effective stochastic gap. That's kind of these constant terms here. And that's how long it takes the algorithm to adapt to whatever setting it's in. So as I mentioned before, as delta 0 tends to 0, this corresponds to just spending longer and longer incurring adversarial regret. So then we ask, well, if we don't want to know what n0 is in advance, can we still learn adaptively and minimax optimally? In particular, we want to be able to match that optimal dependence of t and n0 that Hedge got in the setting when it was told in advance what n0 was. We also want to get the optimal dependence in the single effective expert case on log n and delta 0. And
I
of course,
have a question. So
yeah.
If you know the n0 beforehand, then in terms of a parameter setting, what kind of a parameter setting are you going to use for Hedge to achieve the
if Hedge knows n0 in advance, then it's going to take a learning rate of log n0 instead of log n. So normally it would have log n here, and it's just going to use it in that way, which basically corresponds to what I was saying earlier, where it can run its algorithm kind of only on the n0 subset because it's told that in advance.
Okay, I see.
So in particular, we want to be able to match that without knowing in advance what the setting is. That's kind of the point. And the reason we're giving this talk is because the answer is yes. And so we use actually two algorithms to do this. The first of these is the workhorse, and then the second is just a slight modification to kind of make it really nice and optimal everywhere. So the first is FTRL care, which I'll describe in a second. And what this does is it gets the right dependence on t and n0, and it also doesn't have to know anything about the setting in advance, but it gets slightly suboptimal dependence on n in the single effective expert case. So we add on metacare here, which just says take FTRL care and boost it with one more instance of Hedge, because Hedge does do the right thing in the single effective expert case. And this metacare algorithm achieves all three of these desiderata. So it gets the optimal dependence and doesn't have to know anything about which setting it's in advance. So what do these algorithms, FTRL care and metacare, actually look like? So there's kind of three key insights on how we're going to improve Hedge to obtain FTRL care. The first is that, as I mentioned, if you know n0 in advance, the learning rate to pick for Hedge is this square root log n0 over t. The second thing, which I haven't explained yet, but you can kind of take my word for it, the regret of Hedge depends heavily on what the Shannon entropy of the weights is. So this is just defining Shannon entropy. And a worst case adversary will force these weights to concentrate to a uniform on this set of effective experts. And so just by definition of Shannon entropy, that means that the entropy will look like log n0. And so then a natural question is, can we take our learning rate to be square root of entropy? Because then once entropy starts looking like log n0, our learning rate's going to start looking like what we wanted to pick when we knew n0 in advance. But this is kind of non-trivial because the weight here actually depends on this learning rate. So this is an implicit equation in terms of learning rate and weight. And so it takes a bit of work to actually show that this is going to work and be a reasonable thing to do. And the way that we're going to do that is using the follow the regularized leader framework, which is kind of a fundamental family of algorithms used in online linear optimization. And they're parameterized by an arbitrary sequence of regularizers that map from the simplex, because we're considering weights over experts, to real values. And they are defined according to this objective function. So they solve an optimization problem, which is that the weights used at time t+1 are the best weights in the simplex of this objective function. So the first term is a linear term here. This is just the expected loss of the experts under this weight distribution. And if we only had this term, we would put all of the weight on the expert that's done best so far. But of course, we want to use these algorithms in cases that are not stochastic, in which case kind of blindly following the best expert so far can do really poorly if you have some adversarial nature. And so instead, we're going to regularize, which just means kind of move ourselves away from having our algorithm get too peaked around any one expert and move back towards a uniform. Specifically, the hedge algorithm can be viewed as follow the regularized leader. And this is quite important in our ability to kind of modify it, is that we can write it using the regularizer, which corresponds to the entropy over the learning rate. And so because we also know what the hedge weights are, which is this exponential update rule, we can say that the solution to this optimization problem is defined by these normalized exponential weights. So now let's introduce what our algorithm is, which is follow the regularized leader with care. So care here stands for constraint adaptive. Obviously, we want to adapt to what this set D looks like, and it's root entropic regularization. So what's changed is that instead of regularizing by the negative Shannon entropy like Hedge does, we're regularizing by the square root of the Shannon entropy. And so that is allowing us to adapt to what this set D looks like. And otherwise, it's just the kind of normal FTRL update. So we're able to prove that using this algorithm, FTRL care, for any constraint set D, it achieves the right dependence on N0. So it's got root T log N0. And then in the single effective expert case, it gets log N to the 3/2. So this is slightly suboptimal. We would hope that this gets a log N instead of log N to the 3/2. And so in order to be minimax optimal everywhere, even in this single effective expert case, we're going to combine hedge with FTRL care by basically considering running one instance of FTRL care and one instance of hedge and treating them as two new experts, so meta experts, and then use one more instance of hedge to kind of aggregate over these two experts. The idea is that we're going to incur whichever one gets better regret, so hedge in the single effective expert case, FTRL care everywhere, plus some extra amount from the fact that we're doing this kind of meta learning. And the point is we can prove that this extra amount of regret is kind of negligible. So in particular, Medicare gets regret that is square root T log N0 when N0 is larger than 1. And then in the single effective expert case, it gets the right dependence, which is just log N over delta 0. So it recovers that from hedge. And then when we have more than one effective expert, it gets this log N to the 3/2 term from FTRL care. But this term is now lower order because we have a root T term showing up. So it actually doesn't affect that Medicare is still adaptively minimax optimal. OK, so now let me just go quickly through two kind of technical aspects of the proof that are kind of nice. The first of these is that we show that FTRL care looks like hedge when you have oracle knowledge. So in particular, using that FTRL care definition, we show that it is equivalent to solving this system of equations, which is exactly that implicit system that we intuitively said is what we would hope. So where the learning rate is equal to square root of entropy over T. And second is that we need some way to show that the weights of the experts that are not effective, so the ineffective experts, are actually decaying sufficiently fast. And the way that we do that is with a concentration of measure result. So in particular, we look at the MGF here of the loss of the best expert. So this I0 is the best expert. And that's the expert that we're going to be competing against with respect to regret. And we compare it to any of the ineffective experts. So this soup is over any of the experts that are not effective. And we get a Hufting style bound. So we get it bounded by a variance-like term and then a bias term. And importantly, we get this to hold even under this kind of potentially quite messy expectation operator, which corresponds to the kind of interplay of the adversary and the prediction algorithm over an entire round or T rounds. OK, so let me kind of summarize everything that I've talked about. First, we introduced a spectrum of relaxations of the Iid assumption. And we did this because we think that data is not going to be ever kind of purely adversarial or purely stochastic. And we want to know what are the scenarios in between and that we can still do well in these intermediate scenarios. And finally, that we don't want to have to know in advance which setting we're going to be in. We characterize what the minimax regret looks like under specifically time homogeneous convex constraints, so a particular kind of spectrum of scenarios. And they depend on two quantities, the number of effective experts and the effective stochastic gap that we've introduced. We formalized what it means to be adaptively minimax optimal. So what does it mean to do well across all of these spectrums without knowing in advance which spectrum you're going to be in or setting in the spectrum? We proved that hedge is not adaptively minimax optimal along this spectrum. And in particular, it has to have some oracle knowledge about the setting that it's in order to achieve the minimax optimal dependence. And then we provided a new algorithm, Medicare, that is adaptively minimax optimal because it performs as well as possible for whatever setting it's in, but it doesn't have to have knowledge of which constraint setting it's actually living in. Okay, thanks very much. Hopefully we have time for a couple questions if there are any.
Yeah, thank you for the great talk. Yeah, let's take a few questions. So actually, I have a question. So when you come up with the so-called meta-care algorithms, so you basically call hedge with two experts. One is hedge, the other is the
FTRL.
FTR. Yeah. So then can you go back to the regret? It looks like you on the regret there are still two terms.
Yes.
Yeah.
So yeah, this first term is kind of the leading order term when there's more than one effective expert, and so this term is no longer leading order. So it's just like an extra constant that's kind of hanging around. And what really matters is when there's a single effective expert, then log 1 is just 0. So this term goes away. And this term goes away, and so all we're left with is log n over delta 0 in the case of a single effective expert.
Yeah. So do you think the third term, the log n 3 halves, do you think that term is essential, or that term can be further removed? So do you have any law about the result?
So we do not have a proof that FGRL care needs this 3 halves, although we are pretty sure that from simulations it does need the 3 halves. But we also kind of after this paper have a slightly better algorithm that definitely does not need this 3 halves here. So this is not like a necessary part. This is kind of an artifact coming from FGRL care, but it does seem to be something that FGRL care has to incur. I
see. So the slightly better algorithm in its regret bound, it will only have 2 terms: the square root of t log n 0 plus the log n divided by delta 0, right?
Yeah.
Okay, I see.
And there's maybe it's worth mentioning that this notation here with the squiggly less than or equal to sign has a formal meaning in the paper. It allows us to say something kind of precisely asymptotically. And so there are other. If you look at the full regret bound that Jeff and Blair derived, there are other terms here. It's just that this particular notation allows them to present like the important asymptotic aspects of it. But you need all 3 terms in order to make a correct statement using this notation. So
I see. And I think it is also a little bit unnatural to have hedge algorithm to call hedge algorithm itself, because in the meta-care algorithm, it's essentially a hedge algorithm on top of the hedge algorithm and the FTRL care algorithm. So do you think you can come up with for example, simpler algorithm? You don't need to do this nested hedge algorithm structure.
So actually the algorithm that I described that kind of improves on this does not need that kind of like second layer of nesting. It was slightly unfortunate that we realized that after we kind of finished the paper, but we'll have forthcoming results with describing what that algorithm does and some other benefits from that.
Okay, that's really cool. Yeah, that's exactly the algorithm I'm looking for. I think it's this one is nice, but the nested structure is a little bit unappealing compared with a simpler.
Yeah, it is slightly annoying for the that single effective expert case to not just have cleanly FGRL care here.
I think at the same time, I mean, I know where you're coming from, like from an aesthetic perspective, but from the perspective of thinking about how these algorithms kind of map on to modeling paradigms, I kind of think about these nested algorithms as sort of hierarchical models. And that's not really a connection that we've entirely, we have formalized in any particular way, but I suspect it could be maybe in some limited range of scenarios, right? So and like, I guess my feeling is that if there were some sort of compositional way to think about these nested algorithms, that would be maybe could be a very nice and general way to think about what's going on.
Yeah, I agree. It's like a two-layer neural network. Yeah. So yes, I think the nested algorithm is it might be appealing in some application scenarios. Yeah, I totally agree. It's just like if you have a multi-layer neural network, it can also be considered as a nested application of, for example, logistic regression or something like that. Yeah. I have another more general question. So this algorithm is for online learning with full information feedback. So have you thought about online learning with banded feedback, for example?
Yeah. So we've thought about that a bit. It's not as easy as it seems. So people have also have banded algorithms that work are like optimal at stochastic and adversarial endpoints. And so we can define obviously our setting just the same in the partial information setting as in full information. It doesn't rely on information the player gets to have this kind of notion of in between IID and adversarial. And we're pretty sure that we know what algorithm will be optimal in between. But it has proved trickier than expected to kind of prove that it actually gets those bound. We've spent quite a few nights kind of banging our heads on that, but we are hopeful that we'll be able to get there soon. But yeah, it's definitely an interesting problem to extend this to the banded setting.
Yeah. I think the expert advice algorithm can be compared with, for example, EXP3 algorithm in banded, right? So,
yeah, exactly.
Yeah, I think I don't know what is the key technical challenges.
Basically, it's the kind of variance and the fact that so basically the EXP3 kind of the way that you can modify that is the same way that we've kind of modified Hedge here in the sense of just change your regularizer to something else, but it's a different type of square root regularizer that you want to use in the bandit setting because you're looking at kind of experts on the n and n0 scale instead of log n and log n0 scale. But then the basic kind of like difference that shows up is that it's more difficult to handle the variance in the bandit setting. And so in this case, we're able to control the variance using that kind of MGF bound that I showed. But that's not sufficient in the bandit setting because the weights don't kind of satisfy that same type of property. They look more like a 1 over a quadratic. And so getting the kind of same dependence to or concentration results to hold for the variance when you don't have access to the other ones is that's basically the barrier.
I see. Yeah, that makes sense. Yeah, I see. Yeah, so just to clarify, in your algorithm, you don't need to know this delta 0, right? Delta 0 is unknown. You don't need to know it.
Exactly. Yeah, we don't have to know anything to tune the algorithm at all with this.
I see. And you don't need a doubling trick to figure out the delta 0. So delta 0 is a...
No, yeah, there's none of that. I mean, basically, the idea is that because it might take me a while to go back to this, but the learning rate looking, well, even here it's kind of seen where the learning rate has this like over square root of t. If you don't do that and you want to adapt to t, you can do that with a doubling trick. You could also potentially get a doubling trick type algorithm to work in this case. It's not like we've shown that you can't. But by using a square root of t type term here that changes over time, we don't need anything like that. We just adapt to what these constraints end up being.
I see. So you're saying that for Oracle hedge algorithm, okay. So suppose n0 is not known, even if you are using doubling trick, you still cannot make the regret of hedge algorithm.
Oh, yeah, for hedge, it definitely can't match match that without knowing n0 in advance.
I see. So the key challenge here is to figure out a way which can avoid the knowledge of n0 instead of delta 0. So delta 0 is not challenging here. N0 is the knowledge of n0 is a key challenge.
So yeah, but basically Hedge is able to adapt to delta 0 in the stochastic case just fine. Yeah. So really the thing to kind of make sure that you don't have Oracle knowledge ends up looking like this n0 term.
Right. I see. Yeah, that's very cool. Yeah. So let's say if we have any other questions from audience. If you have questions, please raise your hand. Yeah, so looks like there is no more question. Maybe I can ask one more question. Sure. It's also a very general question. So this is for online learning. And do you think this kind of a square root entropy regularization can be applied in, for example, reinforcement learning or
So
some setting? Yeah.
I guess in reinforcement learning, it will probably rely on the bandit algorithm more than the full information algorithm, I guess I would expect. And so in that case, the regularizer will probably not look like a square root of Shannon entropy. It'll look like a different type of regularizer that's more tuned to the basically bandit setting. But I expect that type, I mean, there's been some nice results recently about kind of using bandit algorithms in the RL setting, I guess. So I would expect that the same type of thing could be extended there, which I think is definitely interesting, especially because in RL, they often aren't as focused on kind of the spectrums in between. It's like usually you're living in kind of an MDP world. And so moving away there would be relaxing the MDP assumption instead of relaxing the IID assumption.
Right. So the immediate step should be how to extend this result to bandit setting. If you can extend it to bandit setting, then you are more optimistic about its application to RL, right?
Yeah, exactly.
Okay, I see. That's very cool. Yeah. So any other questions from the audience? Okay, so if there's no questions, let's thank the speakers again, and please do follow up with Dan and Blair and Jack if you have any other questions later. You can follow up with them by email. Thank you.
Yeah, thanks very much
for having us.
I will stop recording.